Hey friends, it's good to be back with you. And today we're going to dig a little farther into differential equations. Now before I get too far, I want to make sure we have all the nomenclature, got all the lingo figured out. When you first get into differential equations, one of the things you're going to notice is there's a lot of classifying and naming of things. And sometimes that gets a little off-putting. So let's get that out of the way first. There's basically three different categories you're going to have to sort out, three different identifiers when you start working with differential equations. And here they are. Is it linear or nonlinear? I'll tell you what that means here in a second. Is it an initial value or a boundary value problem? And is it ordinary or partial? Okay. Let's do this first. A linear differential equation has a very specific form, and a surprising number of differential equations you'll see are linear. In my work, I spend a lot of time working on vibrations and acoustics, and a lot of the equations that describe vibrating structures are linear second-order ordinary differential equations. So that one specific kind I see quite a lot. So here's the form of a linear differential equation. Looks like this. Oh, there we go. So this form right here, so it's a function of x times y, a function of x times y prime, a function of x times y double prime, and so on. Now, ax and bx, these functions, all these different functions here, those don't have to be linear. The important thing to see here is that y and y prime are never multiplied by each other. You always see them just by themselves. That's what makes this a linear equation. Like I say, if you're working with Newton's laws, things that vibrate, that sort of thing, you're going to see a lot of these. A lot of what you find are linear. Anything that doesn't obey this law, that's nonlinear. So the next one, is it an initial value problem or a boundary value problem? Well, initial value problems are just what they sound like. You're moving through time or you're moving through space, and you know where you started and you don't know where you're going. So for an initial value problem here, my eraser, if I hold it like this, and let's say x is downward, because I can use any coordinate system I want, x is downward and I drop it. I know what the initial value was. I know it was here, that was its initial position, and I know its initial velocity was 0. So with those two pieces of information, I can start marching forward through either time or space and explain what happens after that. Now, let me give you an example of a boundary value problem. This is just a chain. I got this at Sears a long time ago, and I've been getting a lot of mileage out of this cheap piece of chain over the years. Well, what if I hold the ends up like this? There you go, you can see the whole thing, I think. I hold the ends up like this. I know where the ends are. What's going on in the middle is described by a differential equation. Right? So I know this end and I know this end. Okay, I have two xy locations, and I'm trying to calculate what happens in between. Well, this is a boundary value problem. I know one end and I know the other. Now this happens to be a boundary value problem in space, but it could be a boundary value problem in time as well. Most of the boundary value problems I see are structural ones, and so you know where the boundaries are in space. So do you know what's going on at the beginning, or do you know what's going on at both ends? That's the difference between an initial value problem and a boundary value problem. So what's the difference between ordinary and partial? Well, these are not my favorite names, by the way, but we're stuck with them. An ordinary differential equation has one independent variable. A partial differential equation has more than one. It's that simple. What you see with ordinary is you'll see things like dy dx, right? So that d there stands for differential, infinitesimal there. And that's how you know you've got an ordinary differential equation. When you see that d there, that means you've got one independent variable. In this case, the dependent variable would be y, and the independent variable is x. So if you see something written out like this, it tells you what you're trying to find is a function of y that solves some equation, and that y is a function of x. Partial differential equation, there's this thing that looks like a backward 6. That backward 6 is also a derivative, but it's a partial derivative. And what partial means is that there's more than one independent variable. So maybe there's x and z or something like this. But when you see this kind of notation, that backward 6 looking thing, that says this is a differential equation, just like that's a differential equation with one important difference. This one only has one independent variable. This one has more than one. In this case, this is called a partial derivative. Partial y, partial x is how you actually say that. So for the purposes of this class, we're going to avoid partial differential equations. We've got enough problems as it is. We're going to learn about ordinary differential equations. Now, if you want to take a deeper dive into this, absolutely do, but that's beyond the boundaries of this class. So there's all the lingo that you're going to need. There's more, but this is enough. I'm actually going to use one more term that I'll introduce later. All right, so let's try this. Let's make a physical problem, and let's see how A, it turns into a differential equation just naturally, and B, how do you solve it? So let's do this. Let's imagine we've got some sort of space probe. It's out cruising along between, I don't know, Mars and Earth or something like that. And so there's a rocket motor back there. And up here, there's some kind of cool space probe satellite. Maybe there's one of those little cars that we're driving around on Mars right now. I don't know, put a little dish on the front of it, maybe. I don't know. There it is, okay? And we're going to we need some numbers. We're going to say that the mass is 10,000 kilograms. The amount of thrust that the engine makes is 10,000 newtons. Big fan of round numbers here. And there's a thing called m dot. Well, m dot is the rate of change of mass. This is actually dmdt, if you want to think about it that way. And that's how much fuel does this thing burn in every second. Well, we're going to call it 4 kilograms per second. Okay, and that number didn't just come from nowhere. There's a thing called specific impulse. Specific impulse is the amount of momentum that can be generated for every unit mass of fuel. And so on this one, I assumed the specific impulse was 300 seconds. And you work that out and you get seconds. That drops out. So if you work out the numbers here, that gives you 3.9 or 3.398 something, and so I just rounded it off to 4. This is a very reasonable number. So let's see. Let's just go to Newton's law. Let's say F equals ma, which is really m dv dt, okay? And what we're going to do here is we're going to figure out what the change in velocity is as time goes by when you run this engine and you're making 10,000 newtons of thrust. Well, F equals ma, right? You just multiply the two numbers. Well, you do as long as m and a are constant. If m is constant, well, F is constant because rocket engines make a constant thrust. If mass doesn't change, then acceleration is constant. But mass does change. That doesn't change real fast. That's a pretty big number and that's a pretty small number. But as this engine runs and starts burning off more and more fuel, the mass really does change, and so does the acceleration. So let's just do what Isaac would tell us to do here, if he was here. There. That's a differential equation, isn't it? In fact, we'll carry this down here. That's a differential equation. Well, that's a constant, that's a constant, that's a constant, that's our independent variable, and that's a slope. So if we want to solve this, what we're going to try to do is we're going to try to find a function, v of t, that makes this true. Now, this is a relatively rare type of differential equation. This has a property, it's called separable. Again, not my favorite name, but this is what we've got. It's a separable differential equation. Well, what does that mean? Separable means you can actually separate this out. I can push all the t's on one side and all the v's on the other, and I can actually directly integrate this one. This is rare. It's very unusual to find one like this, but this is a pretty good introduction, so let's do that. So let's do some algebra and see if we can make this work. There we go. Now, m dot, when you look at that dot, you think, well, that's a derivative, isn't it? Yes, it is. But m dot is a constant. Okay? It's rate of change of mass, but it's just a number. It's not a function. So this when I integrate, there's no t lurking inside that m dot. This is the only t I have to worry about. Well, I got all the t's on one side with a dt and just dv on the other side. Well, what do you do? Well, there's the algebra part done. Let's do a little calculus. There. I'm going to go from 0 to t. Well, t0 to t, but we'll call that 0. And v0 to v1. Well, that's delta v, isn't it? Huh. If you spend much time reading on astronautics or rockets or things like that, you see delta v a lot. Because a lot of times you don't care how much fuel you have. You care about how much change in velocity that fuel can generate. That's a much more useful number. And so if you listen to NASA audio of missions or things like that, you'll hear about delta V a lot. In fact, a long time ago, when the shuttle was still flying, they tried out this little, not really a rocket pack because there wasn't any combustion, but they were shooting, I think it was CO2 through these little nozzles to make thrust. And so the astronaut went out untethered from the shuttle, just out by himself with this little, well, it wasn't really little, but this giant pack on his back, and could with controls on his, that he could reach with his hands, could go through to maneuver around the shuttle. And if you listen to the audio from that, they don't talk about how much fuel, how much propellant he has left in his pack. They care about how much delta V he's got left. Because obviously the thing they're worried about is he's out scooting around. Can he get back to the shuttle? Because if he can't, they're going to have to go get him. So delta V you see an awful lot. This is very common. And what about this? Well, can you integrate that? Yeah, you can. There's a closed form integral for that. The interesting part, when I tried to do this using MuPad, using both MATLAB and MathCAD, both of them failed, and failed for a surprising reason. But it turns out if you just run this through a numerical integrator, it's no problem. You get the right answer. So this is a separable differential equation. Let's pretend we don't know it's separable. Let's go ahead and figure out how to solve this numerically. Well, there's a bunch of different ways to do this, but the simplest one by far is something called the finite difference method. And what I'm going to do is I'm going to go back and get rid of this. Actually, I'll probably get rid of that too. All right. Actually, give me a second. I'm going to move this up here. This is a state school, so I can't just click and drag. I'm going to have to recopy this. Okay, there we go. If I was at Harvard, I'd have some crazy smart board where I could just do that, but here we are. Anyway, what's a finite difference derivative? Well, finite differences is this. It's really simple. There. Remember, these are infinitesimals. The only way to get those dv's and dt's to go away is to integrate. Well, sometimes problematic. In this one case, it wasn't. But most of the differential equations you see, very seldom do you see a separable one. So getting to just integrate, that's a treat you don't normally get. So what we're going to do is we're going to approximate this with this. Now this is infinitesimal. We don't know what values dv and dt will have. The only way to get these to go away is to integrate. So what I'm going to do is I'm going to approximate it with this. This is almost the definition of a derivative. The only thing we've done is take away that limit as delta t goes to 0. In this case, delta t is not some infinitesimal. It's a number. We know what it is. Okay, we're going to assign it. So what that's going to do is that's going to make this differential equation turn into algebra. Very handy. So let's try it. Okay, there we go. Well, what is it we're trying to find? Well, if we knew what v of n was, could we find v of n plus 1? Sure. Remember, this is an initial value problem. So we've got some initial velocity, and we're trying to find what velocity is at the end of some amount of time when the engine was running. So what I can do now is I can solve this little expression for v of n plus 1. And there we have it. This is how we're going to work this out numerically. We know what v initial is. They'll know. Now, since we're only looking for delta v, we can actually say v initial is 0. We can use any coordinate system we want. If the coordinate system happens to be moving, that's fine. So I'll probably say v0 equals 0 because I don't want to know the absolute velocity. In fact, if you're out in space, absolute velocity, what is that? You have to reference it to something. So since I only want delta t, I'm going to say Vn equals 0. And I know what f is. I'm going to assign a delta t. I'm going to know what that is. m0 I know, m dot I know, and t I will know because I'll know delta t. I can step through in steps of time. And every time I do that, I'll find the next velocity. Go back around. Index this by 1. Find the next velocity. Index this by 1. Find the next velocity. So easy a professor could do it. So you know what that's got to be like. So before we go to my computer and make some numbers come out, let's review a little bit. There were a couple classifications we were interested in: linear versus nonlinear differential equations, initial value problems and boundary value problems, and ordinary or partial differential equations. And then finally we talked about separable ones. So there was basically 4 categories we're messing around with. This is an ordinary differential equation. The only variable here is t. There's only one independent variable. So it's an ordinary differential equation. Is it linear? Yeah, it is. Okay. There's my derivative. There's a function of my independent variable. So this one's linear. And is it an initial value problem or a boundary value problem? What's an initial value problem? I know what the initial velocity is. I have no idea what the end velocity is. That's kind of what we're trying to find out. And the last one, this is separable because this is one of those very few that you can directly integrate. So with that in mind, let's switch. Let's go over to my computer and let's go ahead and grind some numbers out for this.